Hi, I'm Mike Holt with MikeHolt.com, and we got another hour going to cover some very interesting code questions that were submitted to me over the time. Do me a favor, go to MikeHolt.com/live, and if you want to submit your questions there, I'll get it kind of bypassed to me if they're related to what we're talking about. If not, post your question, and I'm going to assemble it and then go ahead and answer it. Now, a lot of people have submitted a lot of questions, and they're like, well, Mike, I haven't seen my answer yet. Well, I've gotten a lot of questions, so I can only go as fast as I can. So let's get going in the program. Just want to take a moment again to thank God for blessing me. And, you know, a lot of people have been blessed. And as I mentioned yesterday's video, a good friend of mine, Joe Sandell in New York City, passed away from the coronavirus. So it's a pretty personal thing for me. And so we just kind of keep his family and lift the family up in prayer. All right. You know, we covered copper-clad aluminum yesterday. And there's an additional question that came in about copper-clad aluminum. Let me just review it real quickly. Copper-clad aluminum is an aluminum conductor, 8000 series, and it's molecularly bonded together with an oxygen-free copper. So this is an actual conductor. So you have copper conductors that we're used to. Then you have aluminum conductors. Then you have a copper molecularly bonded aluminum conductor, and it's copper clad. And the question was, and by the way, you can see it. Here is a 15 amp circuit, which is a 12 gauge copper clad aluminum. Here is a 20 amp circuit, which is going to be a 10 gauge. And then, of course, you have all the different conductors. And you'll notice that each conductor it's a great one here to see. If I can zoom in, I'll try to see if I can zoom in on that. Ooh, look at that. Each conductor is going to be aluminum with a copper molecularly bonded conductor on the outside. And then you do what? You just simply add a bunch together, make it stranded, and then let's go over to maybe this 500 thousandths. Now, the question came up is like, well, let me just get a little history here, and I apologize, the slide kind of caught me off guard. I just got this slide from Peter Gracer, and he's with the Bimetal Association. And he was telling me why copper clad is back and the history of why it came and left. All right, let's take a look at the Civil War. This means copper, this is adjusted for inflation. Copper in the Civil War was $8 a pound. Why Civil War? A lot of, I don't know if they used bullets, copper then, whatever it was. And then we come over here, World War, and then it goes down to about maybe 350 or something like that. World War I came out, a lot of bullets, needed brass, so copper became a premium. And then after the war, guess what happened? Boom, gone. Then you had the Korean War back in the 1950s or something like that, somewhere in there. And then in the 60s, we had the Vietnam War, again, bullets. And then we had some more things going on. This is where the CCA enters. That's a copper-clad aluminum entered the code. It entered the code anytime copper is worth more than $2 a pound. So these guys are like, new technology came in here, boom, copper-clad aluminum came in there. I ran and used copper-clad aluminum in Romex. Then all of a sudden, the war ends. The Vietnam War ends. Boom. Copper goes down. Nobody's buying copper-clad aluminum anymore because it's really not that cost-effective. So the market collapsed, and they no longer sold copper-clad aluminum. Everybody just went out of business, and it was done. And then, so that was back in the or just before the 80s, in the 70, 75, 80 right in there. It was, and then it kept going down, down, down. So there's no market for copper-clad aluminum. And then what happens? All of a sudden, the ETC event takes place. And I don't remember what the ETC event is. That's where the copper mining companies and other organizations kind of created a consortium, or they kind of created I forgot another word I used yesterday, and they decided we're going to fix the cost of copper. And guess what they did? They went ahead and they jacked that sucker all the way up. Now the Bimetal Association said, hey, you know what? That copper is going all the way up there. It's definitely more than $2 a pound. It's time for us to get back in the market. And that's what it is. So copper-clad aluminum is back in the market. And since now you have a cartel, that's what it was. You have a cartel that is going to fix the cost of copper. It's no longer be a free market. more than likely, copper clad aluminum is going to be around for a long time. So just information, what was going on. Now, the question I got after yesterday's recording was, where would you use copper clad aluminum? Okay, well, that's a really great question. I said it yesterday, but there was a lot of things happening involved in that previous video. Okay, aluminum is cheaper than copper clad aluminum. And I have no problem with using aluminum at all. I think aluminum is a great wiring method. You have 3 conductors: copper, aluminum, and copper clad aluminum. So to me, I would use aluminum every chance I could. But there might be some scenarios where you have equipment that says copper only. Well, if it says copper only, you cannot use aluminum, but you could use copper clad, because a copper clad conductor is identified and listed to be suitable to be terminated in an aluminum terminal or a copper terminal. So if it's copper only, 100% I'm in copper clad aluminum. I mean, that's where the market would be. It's lighter, it's less expensive. So basically what copper clad aluminum is going to do is it's going to push copper out of the way. I mean, I can't even imagine. I cannot think of a scenario where I would ever use copper conductors in an installation. I know my buddies in the Copper Development Association, like Mike Holt, we thought you were a good guy. I'm just honest, giving the information. So copper clad aluminum is not going to replace aluminum. Copper clad aluminum, however, might replace aluminum in underground installations, because when you run an aluminum wire underground, you get that little nick in there. Well, then all of a sudden you have the nick in the insulation. It goes, moisture gets in there, and then it destroys. And we've had case people getting killed from that. So underground installations, copper clad aluminum, I think would replace aluminum. Copper clad aluminum will replace copper in every scenario that I can think of. So that's when I would use copper clad aluminum. And make sure you go to mikeholt.com/live and post questions and watch the graphics that we're working with. All right, low voltage dimming control conductors. I covered that a few videos past. And here was the question: Mike, can I run 12-2 MC cable to power the lighting circuits and using the 12 gauge wire for the dimming control for lighting? I'm like, I don't know. So I had to do some research, and my gut feeling was telling me no. But of course, why would I say no? I mean, it makes no sense at all. More than likely, that wiring for the dimmer is going to be a class 2 or a class 3 circuit. So automatically, you would not be able to put a class 2 and a class 3 circuit in the same cable or the same raceway with power conductors. But there is a rule that says, look, let's get into the graphic here. 725.130 says this, parent A, class 1 wiring methods, class 2 and class 3 circuits, typo there, are permitted to use class 1 wiring methods in accordance with 725.46. Now, if you don't know what a class 1, a class 2, and a class 3 circuit is, you are totally lost, and I'm probably not going to help you here. That's covered in my textbook, The Understanding the National Electrical Code, and I explain all the classifications. So I'm assuming you have that knowledge. But a class 1 circuit, just rough, is basically power. It's your power conductors. A class 1 circuit is power. 600 volt rated conductors. Class 2 circuit is limited in power and limited in voltage. Class 3 allows you to raise up the voltage a little bit, but still limited in power. So class 2 and class 3 circuits, we use CL2 cable, CL3 cable. There's other substitutions I'm not going to get into. And so those conductors, a class 2 circuit is rated for 150 volt insulation. A class 3 cable has a 300 volt insulation, and they cannot mark that voltage ratings on the cables, because people might think, oh, it's a 150 volt cable, class 2, and maybe think they can use it. Oh, it's a 300 volt rated insulated cable in class 3, and think they can use it. So there is no marking on voltage of the cable. That's required by 725. Class 1 circuit, however, is what you would normally use as power. It's going to be your 600 volt conductors. It's going to be Romex, MC cable, AC cable. It's going to be pipe and wire. It's going to be, you have to make splices and boxes. See, if you're in a class 2 circuit, a class 3 circuit, you don't have to comply with the requirements contained in Article 300. So there's a lot of, you just run a cable for your low voltage thermostat, your controls, everything is fine. But in this case here, we want to have dimming control of the lighting, and we want that control to be in the switch, and I need to get those conductors up to the lighting for the controlling, and it's like, oh, So can you use 12.4 MC cable? Yes, because there's a rule, 725.130A exception 2. And it says, look, if you want to, you can reclassify that class 2 or class 3 circuit as a class 1 circuit. But if you do that, then you're going to have to go to chapter 3 wire methods, which is going to be 600 volt rated conductors. So 14.2 MC cable, those two conductors, it would be a class 2 circuit reclassified as a class 1 circuit. And there's a rule that tells us that you can have class 1 circuit conductors with power conductors where they are functionally associated. So yes, that could be done. Now, the easiest thing, and not be a dinosaur, is just go out and buy a cable. Buy MC cable that has your hot and your neutral and your equipment grounding conductor, and it has a twisted pair conductor. Now, these conductors, however, are not 600 volt rated. They're going to be class 2. I don't know if they're class 2 or class 3. But the code says this: you can never have class 2 and class 3 conductors in the same raceway or cable with power conductors unless they're separated by a non-metallic covering. And I give you an example of non-metallic covering. Romex. Romex is a non-metallic covering around your phase conductors and your power conductors, or whatever you want to call it, phase and neutral. Okay, so Romex is a covering. You know what they did? This is like the coolest thing in the world. The outer jacket of this type of cable here is Romex. Is that the coolest thing in the world? They said, well, look, you can't have control wires in the same raceway or cable with power wires, but you can have control wires within a non-metallic sheath, and that then can be adjacent to power conductors. So if you're trying to control any kind of dimming, Southwire, I'm sure other manufacturers make this. This is the way I would go. So hopefully that helps you put that in perspective. But you could use 12.4. Bonding bushing requirements for branch circuits and feeders. All right. I'm having an issue with understanding when I need to install a grounding bushing. He said grounding bushing. You know what? I don't know what the heck you call those things. Are they bonding bushings? What rule would I look for on that? 250.97. Let me go to 250.97, and I'm wondering if we call that a bonding bushing or a grounding bushing. 250.97. For circuits of over 250 volts of ground, the electrical continuity of metal raceways and cables with metal sheaths that contain conductors other than service conductors. See, service conductors is 250.94. Shall be insured by one or more of the methods specified in 250.92b. Well, it's 250.92, not 94. 92b, except b1. So I have to go to 250.92b and 250.92b. I'm just looking, what is it called? Is it called a grounding bushing or a bonding bushing? I'm sure it's called a grounding bushing if you look in a catalog. I would have called it a bonding bushing. 250.92b methods, bonding jumpers needing the requirements of this article. Okay, so the code doesn't give it a name. They just talk about the bonding jumper. You'd have to use a fitting that would meet that requirement. Let's go back to the question. I'm having an issue with understanding when I need to install a grounding bushing, which is probably the right term, for branch circuits and feeders. Well, 250.97, which what I was reading. It's easier to read it in a graphic than it is to actual code book, but you want to make sure that you watch this video again and again and again. Make sure you get your code book out. You know, make sure you get educated. You're the leaders, right? You're the ones that's protecting the public. If you don't know basic code, who the heck's going to know the basic code? There we go. 250.97. Metal raceways or cables containing 277 or 480 volt circuits terminating at ring knockouts. Look right here. Let me see if I can zoom in again. You can see a little air gap right there. Right? At ring knockouts must be bonded with a bonding jumper size per 250.122. based on the rating of the overcurrent device. So when do you need a bonding bushing and a bonding jumper? If it's not a service, it's 277 or 480 volts, and you're going to a ring knockout. If you're not going in a ring knockout, well, then no bonding bushing is required. Twice now I've had the issue brought up about transformers, and I've commented at least twice in previous videos that it's a common practice in some parts of the country, particularly the Northeast. I know in New York City, a lot of guys are like, well, that's not New York City code. Of course it's not in your code. You guys just do it and you got to justify it. So you say it's new. Now that, think about a transformer. They put bonding bushings and bonding jumpers on the end of a transformer when they're running flex. Like, what the heck would that do? It's flex. The flex is not an equipment grounding conductor, so that serves no purpose. You'd have to have an equipment grounding conductor within the flex. So no, you don't put bonding bushings and bonding jumpers on the primary or the secondary side of the transformer unless you went into concentric or eccentric knockout. So it's possible that at the panel where you made a connection, there's a ring knockout remaining. Well, then you'd put a bonding bushing and bonding jumper at the panel, never at the transformer, unless there's ring knockouts on the transformer that are remaining that I'm not aware if that's really the case. Now, why do we need bonding bushings and bonding jumpers on 277 480 volt circuits, and we don't have to have those if it's going to be a 120 circuit or 208 or 240? Look at the logic here. Now, this is just a concept that let's assume that you had a 120 volt fault and the contact of that fault is 1 ohm, which is quite high. Then what would be the heat? This is all covered. Basic fundamental theory, guys. Make sure you have that theory. Completely watch the videos at least 2 to 3 times. Heat is a function of I squared R. I is the intensity of the circuit, which we measure it in amperes, squared, times the resistance of the circuit, which we measure it in ohms. So if we take, okay, we know the voltage, we know the resistance, we got to calculate the current. I is E over R, 120 divided by 1 is 120 amperes. Heat is a function of I squared R. So we take the 120 squared times the 1 ohm, that gives me 1,440 watts of power. We're just saying, using an example to compare one thing, that's 1,440 watts of power. Now, what about if it was a 277 volt fault with the same amount of resistance, 1 ohm? Well, the current's going to be calculated E over R. E is electromotive force over the resistance, 277 divided by 1, 277 amperes. And now the key here is what? Heat is a function of I squared times R. It's 277 squared times 1 ohm. Look at the amount of heat that would happen on a 277 volt, 1 ohm resistor fault event. So you can see that you a little bit more than double the voltage, and because it's by the square, you're going to be doubling the voltage and then you're going to square it. So right here, you go from 1,440 watts of power in a 120 volt fault. Those rings, those knockouts, they're designed for 120 volt faults. Those rings, those knockouts are not designed for 277 480. So if you're running 277 480, you go to a ring knockout, you're always going to put a bonding bushing and a bonding jumper, and you size that jumper per table 250 122 based upon the rating of the overcurrent device protecting the circuits within that particular raceway or cable. That's when you put bonding bushings and bonding jumpers. No, you don't put them on transformer secondaries or transformer primaries because there are no ring knockouts there, so it doesn't apply. Now, they do make boxes. I call them not knockouts, I call them punch-outs. And the boxes are really cool. I really like what the manufacturer's done. They've actually marked in the box suitable for 277/480. So when you get these kind of boxes, this is not a knockout. This is not a ringed knockout. This box is specifically listed and identified for a 277 480 volt circuit. So no bonding jump, no grounding. What's it called? No grounding. What do you call that? No grounding bushing, which is probably the most correct term, and no bonding jumper. Or more importantly, no bonding jumper, because you have to have the bushing to make it happen. All right. And here we go on that transformer, clearly putting bonding bushings and bonding jumpers on fittings where the wiring method is supplied by flex metal conduit, and then placing an equipment grounding conductor within that raceway makes totally no sense. Okay, Mike, is that a code violation? No, you can put extra wire in there. Here's my problem with this, that you guys think it's supposed to be required. that means you don't know the code. And it bothers me that if you're the expert, you're the leader, you're the electrical contractor, you're the guy, I mean, you're supposed to be the boss. Come on. You're the instructor. You're teaching guys, put bonding bushings and bonding jumpers on transformers. Some young guy who's studying the code, watching this video, is going to go to your class, eat your lunch, and say, what the heck are you talking about? This is ridiculous. You look bad. That's all I'm trying to say. If you're an electrician, you're spending money and time of your boss's money and time just because you think so. Guys, let's just make sure we know the physics. Let's make sure that we know the code. Let's install it. Let's make it safe. Let's protect people. So, nope, none of these bonding bushings and jumpers are there. Brian, you got a comment there you want to jump in on?
Yeah, Mike, got actually several comments here. So one of them is from Ron. He says, bonding jumpers don't make sense if you have to use 240 versus 120 because it would be 240 would be close to the 277 volt heat. So maybe you want to address 277 versus 240 volt and why you don't need it for 240.
Okay, the questions, well, you guys heard the question there. Listen, guys, when you're talking about a fault to an enclosure, you're not making a 240 volt fault to an enclosure. A 240 volt fault is called a short circuit. So if you had a 240 volt fault, that means you're having a short circuit. That's why it doesn't apply at all. So you can't say, well, 240 is kind of close to 277. No, it's not, because you're not having a 240 volt fault. You're having a what? A 120 volt fault. Brian, does that make sense?
Yep, definitely makes sense.
It's line to neutral, guys.
Yeah.
These are ground faults, guys. Ground faults are line to neutral faults.
I was just going to say, I think a lot of times we forget line to line versus line to neutral when we're talking about voltages. As electricians, we're just, everything is 120, 240, 277, 480. And that the key there is that when you're talking about a ground fault, right, it's a phase conductor. Go to Article 100 definition. It's a phase conductor going to the enclosure. It's a line to ground fault, not a line to line fault. Yeah,
that's a short
exactly.
Circuit. Okay.
Got another comment. This is from research. Grounding bushings and jumpers are required for all conduit terminations in classified areas. Just a note there.
Oh, yeah. Research. Our research. That's right. One second. Don't tell me. That's 250-100 tells us to go of any voltage that you have to go to chapter 5. Let me see what it is. It would be 5 for class 1 divisions. 501.30a talks about you have to put bonding bushings and bonding jumper for classified locations from the point where the fault would take place all the way back over to the service or the separate drive systems. Class 2 is 502.30, same rule, and Class 3 is 503.30. So research, thanks. This is a great. Yeah, I wasn't thinking about Chapter 5. Where else bonding bushing? That's it. For branch circuits and feeders. And at services, you put it on certain cases, and we haven't covered that yet. All right,
yeah,
Brian,
I got another really good
one.
This is a really hot topic here.
Really?
250.97 grounding bushing question. I fully agree if you use a raceway as a GEC, you would need a grounding bushing. Do you still need a grounding bushing if you pull a separate grounding electroconductor?
Here's what he was saying. Mike, let me see what he was saying. If I have a raceway and it's a metal raceway, is that the question? It'd be a metal raceway, right, Brian? And you're pulling an equipment grounding conductor in there, and you're going into ring knockouts. Okay, there you go. You run an EMT, you're going into ring knockouts, and your specs call and require an equipment grounding conductor to be installed in each of the raceways, right? So if your specs call that, now you have an equipment grounding conductor in the raceway, but you have a raceway it's 277 40 volt circuits in there. Then you have a raceway containing an equipment grounding conductor. Let's go to 250.97. See, here's the beautiful thing about the code. It says what it says. Not what you wanted to say, not what you thought it was going to say, but it says what it says. And so if you're wondering, well, what about this, what about that? The code is like so linear, it's so simple that it's not that complicated. Here's the problem. You want it to be something. Somebody told you something, so you already have in your mind like, well, wait a minute, if I ran EMT and I put it in a ring knockout and I pulled an equipment grounding conductor in there, why do I have to put a bonding bushing and bonding jumper on there? That doesn't make any sense. Stop. Stop. We're not asking you to make sense, because who knows what the heck's going on in your brain and what you think is sense. I don't get involved emotional. I don't give opinions. I just simply go to the code book. Let me read you the code book. Let's see what it says here. 250.97. For circuits of over 250 volts to ground. 277, right? The electrical continuity of metal raceways and cables with metal sheets that contain any conductors other than service conductors, any conductors, shall be insured by one or more of the methods specified in 250.92b. Then you have to go to 250.92b, and that's going to get into your bonding bushings and bonding jumpers. Done. So do you need a bonding bushing and a metal raceway containing 277 volt circuits terminating in a ring knockout? Yes. But what about if I put an equipment grounding conductor in there? Is it a metal raceway? Yeah. Is it going into a ring knockout? Yeah. Is it 277? Yep. Then you need a bonding bushing. That doesn't, whoa, stop. Don't even want to hear the crap about it. Doesn't make sense. You know why? When I was an electrician, I would read all these code rules, and it didn't make any sense to me. And so I started getting in the process and submitting public inputs, suggesting the changes. By the way, my very first time I ever submitted changes to the code, I submitted 175. Some people still remember this. Guess how many I have approved? None. Last code cycle, I think about 400, probably had about 180 approved. So do a little bit better in there. My point is this. There's a lot of stuff you don't know about. There are a lot of different variables that you couldn't even possibly conceive. And maybe it would be okay, but the other thing is, well, Mike, if there's a fault to the raceway, it's going to go over to the ring knockouts. And that's where you're going to have your fault. Because you don't know that equipment grounding conductor is always going to be there. Well, who cares? The code says you need it in there. Done. Brian, anything else?
Yeah, just one last comment I got from Steve here. He said the manufacturers called the bushings metal insulated grounding bushings on the containers.
Well, it's not insulated. So that's only if you got that bushing that was insulated. See, would it be insulated? Well, if it's 4 gauge and larger, it has to be. We're going to talk about that a little bit. Okay, so let's forget the word insulated. Brian, read it to me again. Metal what?
It's metal insulated grounding bushing.
Okay, that's what I figured. It's a grounding bushing. If it's insulated, it's insulated. All right, I'm done, Brian. We're good?
All set.
All right, I'm moving on. Plastic bushing requirements. You know what I don't know? When is a plastic bushing required? I didn't add this question, but I'm going to add it myself now. When the heck do you put in a plastic bushing? Like that. Do you put that in before you pull the wire and then you destroy the bushing when you pull the wire in? And the rope and the cable? Do you put that in after you pull the wire? Do you put that in after you've pulled the wire and made up all the fittings, and then you just kind of like take your dikes and cut the back of it and slide it on there and put it in the back? I do not know when. And Brian, make a note for me. I think we have a note there. I want to make a public input to say that has to be there maybe before you pull the wire. I don't know. It has to be there at some point. I don't know. But let's assume it has to be there. Well, we know it has to be there. Don't know when. Here it goes. Here's what the code says. Now, there's a G1 and a G2. So the G says that you have to protect the conductors if they're 4 gauge and larger, and it gives you some options. This is one option of doing it, which is the option that we've been doing for 100 years, I think. Insulated conductors 4 gauge and larger that enter an enclosure must be protected by a fitting providing a smoothly rounded insulated surface. Now watch, this is 4 gauge and larger. Well, Mike, what about 14, 12, 10, and 8? Well, if it's fittings, the listing requirement of fittings requires that the fitting be constructed to provide a rounded surface. So because it's a fitting, 14, 12, 10, and 8 fittings do not have to have any kind of insulated or protected bushing. But if you go 4 gauge and larger, then the fittings are like, hey, listen, we're not providing any kind of protection at that point. 4 gauge and larger, you can put a plastic bushings, which is what we've done. And the 2020 code added this fitting And when he added this fitting to the 2020 code, I'm like, yeah, whatever. I just blew the whole thing up. I thought it was, I don't know what the heck to talk about. They're talking about a metal fitting. The 2020 code says you don't have to use a smoothly rounded insulating surface. It says you can use 4 gauge by a listed metal fitting with smoothly rounded edges. It's different than smoothly rounded insulating surface. It's just smoothly rounded edges. And I'm thinking, I'm going to go out now and buy these metal smoothly rounded edge fittings. For the conductors, number one is like, man, I don't know about that metal thing. But I guess if it says here, it's listed, so I guess however they do it, I guess you can. But you know what's cool about this thing? This is really cool. I would never be getting, ever again, I would never be using plastic bushings. I'm going with these metal, smoothly rounded edges bushings. Let me tell you why. You don't need a lock nut. You can put that in before you pull the wires, which kind of makes sense as to why we would have it in there in the first place. So you save a lock nut, you put it on there, it's mechanical, it's solid. You pull the wire in there, and that's the coolest thing in the world. Brian, you got a video? Brian, can I see you there? Can you go ahead and
yeah, I've got video? A great video for you, Mike. Here you go.
I can't see it. Brian, is it playing there? Brian, is it playing? I guess Instagram, you're not going to see this video, and it's a very cool video. So what I suggest you do is go to mikeholt.com/live, go to Facebook, see this video. I didn't know this playing. Are we done now on that video, Brian? Okay. I couldn't see it because I'm streaming live with Instagram, but I've seen that video and I asked Brian to play it for you guys because he's playing it. I think that is just so cool. So that was a 2020 change. Now, I mentioned this. If it's going to be, actually it was 4 gauge and larger, which means 14, 12, 10, 8, and 6 does not have to have a bushing if it's going to go to a fitting. If it's larger than 6, 4 gauge and larger, you're always going to have an insulating bushing or a metal with smoothly rounded edges. Those are the two ways that you can meet that. Now, there's an additional time which you have to put some kind of protective bushing on, and that would be if you go to rigid metal or IMC. Anytime, where's the raceway at? Right here. If you have a raceway entry in an enclosure, a raceway entry, not rigid conduit with a connector. We're talking about threaded rigid metal conduit, IMC, going directly into the enclosure. Then regardless of the size conductors, it could be 14, 12, 10, 8, 6, you're going to have an insulated bushing. So that's going to be in 344.46 as well as 342.46 for IMC. Okay. Brian says we got some comments. Okay, I'm ready here.
All right, yeah, we got some good ones here. Okay, on installing the bushings before you pull conductors.
What do you got, Brian?
Wouldn't 300.18 imply that they should be installed prior to conductor installation?
Brian, I'm not hearing you. The question, okay, everybody got that question, right, Brian? Okay, so you got the question. We got to go to 300.18 and saying, well, Mike, don't you have to put that bushing because 300.18 says it? I don't know. Never thought about this. 318 says that basically you have to have an installation complete before you can pull the conductors. It says raceways, other than bus bars or exposed raceways having hinge or removable covers shall be installed complete between outlet junction or splicing points prior to the installation of conductors. Let me read this again. Raceways shall be installed complete between outlet boxes, junction box, splicing points prior to the installation of conductors. Nope. You got to put the raceway in complete before you pull wire, but you don't have to have a bushing on there. They didn't say raceways and associated fittings. It just simply says what 318 is saying. Listen, guys, I did this one time. Actually, I didn't do it. I was a journeyman electrician time. I went to a high-rise, 7-story high-rise building, and it was in North Miami Beach. They pulled all the wire for all 7 stories, and they hadn't even finished up the 4th floor forming yet. So I get to the job. I don't know anything about this. I'm just seeing all this wire at every apartment just piled, sitting there, with like some PVC run up to like the 2nd floor and some run up to the 2nd floor, and then wires pulled to that spot and just kind of hanging on the floor there. And then you had all this wire all over the place, and I'm like, why did you guys pull all this wire and have it all hanging in the 1st floor and people rolling stuff over it and wheelbarrows and walking on it, the whole thing getting a big mess? They said because the owner wanted to pull that wire because he wanted to finish up the switch gear because he got a draw on the gear. And I'm like, okay. Now, I don't know back in 1973 whether 300.18 was there at the time. I can guarantee you in 1973, if it was there, I didn't know it was there. But not really mattered because I wasn't the foreman. I was just a guy working on the job, just came on the job. So 318 is talking about you have to complete the raceway installation. I don't believe, if you want as an inspector and you want to use that as a basis, whatever. Okay. Okay, Brian, anything else?
Oh, yeah, Mike, we got lots of other comments here. This is a hot one.
Lots of comments. Like, what's the big deal about a bushing?
Okay, do you need a plastic bushing on a terminal adapter for PVC?
I have PVC. It's a raceway. I'm putting it in a box, right? Well, if we go back over the 300.4G, it didn't say for rigid metal, for EMT. It didn't say anything. It just simply says, let's read it again. Insulated conductors 4 and larger that enter an enclosure must be protected by a fitting providing a smoothly rounded insulated surface. Now let's talk about PVC. PVC for conductors 6 gauge and smaller are constructed specifically according to the listing requirements and the standard to protect conductors 14, 12, 10, 8, and 6. So they're specifically designed for that. Once you get larger than 6 gauge on any wiring method, it doesn't matter whether it's PVC or not, then you have to have that bushing or that protective metal bushing. You can put a metal bushing, I guess, on PVC too. You have to protect it. So let's get an understanding here. The product standard for fittings for 6 gauge and smaller, that is what the fitting is listed for. If it's larger than 6 gauge, it's not listed to protect conductors larger than 6 gauge. So this isn't like, I know there was something going on in the industry about PVC and all kinds of stuff. I'm like, what the heck are you guys talking about? It doesn't matter if it's EMT or PVC. The rules don't change because the fittings standards are exactly the same. So if you have 4 gauge and larger, you are putting some kind of protective bushing, whether it's plastic or metal.
Okay, Mike, got a couple more. One comment, hey, Mike, they make hinged snap-on bushings. So that's an interesting comment.
Well, they make hinged snap-on bushings, and actually they make them, I don't know if they make hinge snap-on bushings that are not grounding bushings, but maybe they do. So there's a perfect example. Like, what happened? Do you have to put it before or not? Listen, the authority having jurisdiction can decide, because I don't know, there is no rule that tells you when you have to put it in, before or after you pull the wire. So whatever the authority jurisdiction 90.4 makes that decision, and whatever they base it on, I'm like, yeah, okay, I'm good with that. That's why I want to submit a public input, because I want to know what the answer is. So if they make these hinge bushings, they make these hinge bushings also with a bonding, it's a grounding, an insulated grounding bushing fitting that's hinged. Okay, but I still don't know when you have to put it in there, before or after you pull the wire.
And I got a couple guys asking about, don't you need a bushing for pipe sizes 1.25 inches and larger?
That's an interesting question. Don't you need some kind of insulated bushing for raceway size 1.25 inches and larger? No. Raceway sizing is irrelevant. You could have a you could have a half-inch piece of rigid metal conduit, and you need with 14 gauge wire, and you need to have a bushing on there because it's not a fitting. It's going to be in 344 dot, what did that was? 344.46 and 342.46. So it doesn't matter. You could run a 2-inch raceway and not have any insulating bushings if the conductors you install are not larger than 6 gauge. Guys, this is not a raceway size. This doesn't matter whether it's EMT or PVC. It has to do with fittings. Fittings are listed for 6 gauge and smaller without any protection. Fittings are listed. They are not listed to protect conductors 4 gauge and larger. That's it. I don't care if you put in a 2-inch raceway. If you're running conductors in that raceway that's not larger than 4 inches, 4 gauge, then no. So I never heard that 1.25 inch one. That's a dinosaur that told another dinosaur, and you dinosaurs are running around telling each other something that, of course, makes no sense at all. No. What else? That's it. Wow. A lot of excitement there on bushings. Guys, 6 gauge and smaller, if it's a fitting, don't worry about it. 4 gauge and large, a fitting, you put it on. Done. But the cool thing is the metal fitting now, which allows you not to have a lock nut. And you saw in that raceway how you can pull those wires all the way through. So that's what I would use if I was an electrical contractor. Ground ring electrode. Oh, man. If you're an engineer, I'm just going to piss you off. And I don't really care. But ground ring. What warrants the installation of a ground ring as a grounding electrode? We talked about the grounding electrode in a previous video. 250.50 talks about that any of these electrodes that are available, that you have to kind of like tie them all together. Let me see if I can remember what the different type of electrodes they are. A water pipe electrode, which really isn't a water pipe electrode because you got to supplement it, but okay. Concrete encased electrode, rebar, right? 20 feet, all those rules there, 4 gauge wire. Couple ground rods, unless you got a ground resistance of 25 ohms or less. There's a listed type of ground fitting you could buy. Maybe some kind of metal underground water pipe structure. And a ground ring. Why would I put a ground ring? Why would I run a copper wire? But you know what? I don't know this. Maybe Peter Gracer, you're watching this. You're on code panel 6. Can I run a bare copper clad conductor direct buried? Is that listed for that? So let's just forget that to the side because I don't know. Why would you run a copper wire all the way around a building when you could just put in 2 ground rods? Or you could just run a 4 gauge wire and just go right to the concrete encased electrode. There is just completely. Why? Well, because somebody wanted to do it, and so the code allows you to put a ring around the building. So does it make a difference? Does it help anything? Listen, go to MikeHolt.com, click on videos, go to grounding and bonding, and watch the very, very first video on that, about 1 hour and 13 minutes. Every one of you that's watching this video, you have to go to MikeHolt.com. You got to click on videos. You got to go to bonding and grounding. Then you have to watch that video, and you'll understand my answer that I want to say inside here. Guys, grounding it's for high voltage transients. If you had a 2,000 amp service, if it was me, 2,000 amp service, I'd run 4 gauge wire, go over to the concrete encased electrode. Bada bing, bada boom, done, finish. I go sit there and worry about anything else like that. That's what I do. But there's engineering, and they run this, I don't know, 500,000 all the way around this building and do all kinds of stuff, and they put access holes so they can get out. Are you kidding me? Go to MikeHolt.com, go to videos, go to bonding and grounding, watch that video, and you realize, I'm not going to say anything, just that you realize that you don't need to do that. Now let's talk about the code. So if you were going to do it, here's what a code tells you. Well, it has to be buried no less than 30 inches. You're going to run a trench all the way around a whole building? and it can't be any smaller than 2-gauge wire. You're going to run a 2-gauge wire all the way around the entire building when you could have put a couple ground rods? Or you could have just gone to the concrete encased electrode? As a matter of fact, look right here. If you go to the structural steel, okay, and you have the structure that has anchor bolts, and you take one piece of rebar in the footer and foundation, and you connect it to one anchor bolt with tie wires, you're done. Oh my gosh. I don't know what to say. Now, what I have here? That's A. Okay, I'm not sure what I have on 52A4. Okay, 250-52A4 says probably that you can use a ring, and all those other references, like you see on the bottom, are 30 inches, and probably the 2-gauge wire size is in 53F. I cannot even conceive the possibility why anybody would put a ring around a building. That's number one. Hang on, I got more stuff here for you. You know what sometimes they do, though? In larger buildings, they have a lightning protection system that's installed in accordance with 780, right? Lightning protection standard. And the lightning protection standard says, in order to protect a building, and this is not an NFPA 780 seminar, it says that you put air terminals on a building to accommodate the 300-foot diameter sphere of influence. So you take this 300-foot ball and you roll around the building and you put air terminals, you design this whole thing, and you get all these air terminals now. And the theory is that when lightning strikes a building, that it's not going to strike the actual building and catch it on fire or cause damage to it, but it will strike one of these little things sticking up. Some people, they used to be called lightning. What, lightning? I forgot what they call them. They're called, no, they used to be called other than air terminals before. And now they're called some striking things. 2020, a few codes, they changed it. Doesn't really matter. What's on the roof, does not do anything with us. Then what you do is you take those things and you tie them together with a conductor, and then you go down to the earth. And when you get this building so large, you're going to have to go to the earth so much distance of conductor length, and then you're going to have to start going to the earth. So now you go a big building, on this corner you go to the earth, the other corner to the earth, the other corner to the earth, the other corner. Then you got a long length. Well, then you start taking more to the earth, and you start driving all these ground rods. All these down leads for these air striking devices go down to a ground rod. And somebody's like, instead of us driving ground round all the way around the building for each of these air terminal grounding conductors going down, we could just run a wire all the way around that building, and then we can go ahead and make the connection of the lightning protection system to the ring. Guess what? That ring is a lightning protection system. You cannot use that ring as a National Electric Code grounding electrode. So if you have a ring around a building and the lightning protection guys are connecting to it, then that is not the ground ring that is discussed in the code book. The ground ring discussed in the code book is when you run a copper conductor. I think it's copper. Did I say copper? Yeah, copper conductor. Ooh, so it can't be copper clad. You have to run a copper conductor all the way around the building, 30 inches deep, no less than 2-gauge wire. Well, who does that? So, I have no clue. By the way, there's another point I want to make here. Whatever the lightning protection ground is, and whatever the building type of ground is, these are two complete different systems, and they have to be done separately and independently according to the standards. The lightning protection ground is 780. The electrical system ground is going to be, it's NFPA 780. The electrical system ground, power ground, is going to be NFPA 70. And you have them installed separately. And then the code book says this, right here, in 250.60, note 2. The lightning protection system must be bonded to the building grounding electrode system. And that gives us a reference to 250.106. So you have to take your electrical system, go find the lightning protection guy's wire, and connect to it. And guess what 780 says? It tells the lightning protection guys, hey, you got to bond your lightning protection grounding system to the building grounding electrode. So you both guys are like looking at each other. And if you're a smart electrician, you're like, hey, buddy, you better make sure you tie your lightning protection system to my electrical grounding electrode system. Then you're done. But if they don't do it, then you have to do it. Let me see if there's anything else. Okay, Brian, anything else? We got
Oh,
comments?
yeah. Actually, I have a comment here from Mario,
Oh, yeah.
and he says, "Hey, Mike, I believe you can run copper-clad aluminum GEC in a raceway underground, but not bear in direct contact with the earth per 250-64."
Mario is saying that 250-64 says 250-64. I need to highlight this. 66 A, B, C. Oh, 64A. Okay, let me read it. 250-64A. Grounding electrode conductors. Yeah, that doesn't apply. 250-64A is talking about a grounding electrode conductor. I was talking about a grounding electrode. So, but there is some reference about grounding electrode conductors. And by the way, the grounding electrode, the ring electrode was already resolved because we saw the graphic here. And it said it had to be a copper conductor. So it's a moot point. But 64A has to do with the conductor going to the grounding electrode. All right, anything else, Brian?
Nope, that's it for this one.
That's it. All right. Hospital grade receptacles. Mike, when are you required to use hospital grade receptacles? Pretty much probably never. Unless you are in a hospital and you're in that hospital. I'm sure probably almost everybody watching this video somehow has been in a hospital or they've been in an urgent care. They've been in there and you're looking and all, your brain just going, you see like all these receptacles along this strip here and you see all the, so when you see all those receptacles, I think there's, I don't remember, 517, 18 or somewhere in there. We'll talk more about that. I think it says you have to have 8 receptacles. Listen, if you are in a patient care area not a patient care area, if you're going to be in a hospital or a surgery center where you're going to have that bed and you're going to be spending the night in it, you're going to have a hospital grade receptacle. Most people are not doing wiring in it. So if you're not in a hospital or a surgery center, you're not staying in a bed like that with all the stuff connected inside you, you would never use a hospital grade receptacle. So let's actually read the language where it says you shall install one. There's the picture I was talking about. If you see that, yes, you need a hospital grade receptacle. If you're in a chiropractor's office, a dentist's office, a doctor's office, and it doesn't have all that stuff inside there because it's not a surgery center, just an office. Let's read the language. Here's what it says in 517.18b. Each patient bed location, key word, definition of 517.2 talks about a patient bed. Each patient bed location requires at least 8 hospital grade receptacles. Now don't misunderstand. I don't know if you see this. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I see 10 hospital grade receptacles. So when I talk about a receptacle, a duplex is 2 receptacles. Okay? Now, if you're talking about receptacle outlets, well, that would be 1 receptacle outlet per the Article 100 definition. That single gang box would be a receptacle outlet, and this would be a receptacle outlet. A receptacle outlet is a box where you put 1 or more receptacles within it. So this code is not talking about the number of receptacle outlets like we had when we had a garage, where you need to have a receptacle outlet for each bay for the vehicles. This is like you need 8 receptacles that are hospital grade. So that's the rule when you need to have it. So if that's when you need to have it, that means every other time you don't need to have it. So if you go, and here's the general care space, the title of 517.18. A general care space includes, but it's not limited to, inpatient beds, that's people going to spend in the night, dialysis rooms, vitro fertilization rooms, procedure rooms, and similar rooms. So, Harley, if you see this and you're doing an installation there, I think you already know, and everybody on the planet knows, and you're in that room right there, everybody knows those are hospital grade receptacles. It's when you're on any other type of facility, So let's say you're in a chiropractic, like look at this graphic here. No, you don't put hospital grade receptacles there. There's not required by the code. So the key here is when is it required? Well, it's when it's not. So if it tells you when it's required, you have to. Every other time, it's not required. It just simply works that way. Brian, anything else?
Hey, Mike, question here. Is a hospital grade receptacle just a red receptacle?
Oh, let me tell you a story about a hospital grade receptacle. I became an electrical contractor in 1975, and I got this housing project. And 75 was a pretty bad time of the country, guys. I mean, it was really, really bad. That's what copper was really, really, really high. Okay, that's when we had oil embargoes. That's when we had rationing of gasoline. That's when there was a price freeze. Nixon was a president. It was like my house, the interest on my house was 19% interest on my home. That was a really bad time. So I'm an electrical contractor. Somehow I got this job. I don't know I had no clue what I was doing. I didn't know how to estimate a job. I didn't know how to run a business. I didn't know squat. But somehow I got this job. And I did temporaries. I thought, you know what? I'm going to put hospital grade receptacles on temporaries. I'm thinking, hospital grade receptacle? I'm a good guy. I'm a quality contractor. I ordered I think it was 20 hospital grade receptacles. Now, I have no clue how much a hospital grade receptacle is. I don't even know what the balance of my checking account is, much less anything. I get the receptacles in. It's all kind of cool. I put it on my temporary job sites and everything. Those suckers are crap. They broke, they got damaged, and then at the end of the month, I got a bill for 20 hospital grade receptacles. I don't remember how much it was in 1970, but in 1975, 76 in there. But I know that it was I was in total shock. So now, there are some differences in hospital grade, and I'm going to give you probably hardly any information. Number one, it has to do with the tension. You know how when you plug something in a receptacle and you pull it out? And sometimes you go in an airport and you're like, is it actually even in there? Is it even making contact? I mean, what's going on in there? So there is the tension that it places on the connections. And that's all I know. So go to the internet, search on hospital grade. Listen, you're not putting them in anyhow, so who cares? Okay? But if you care, that's what it is. I know they're super expensive. I know the question.
Yeah, Mike, one of the guys is like, okay, but chiro and dental will require medical grade wiring though, right?
Well, Mike, your wiring, I'll tell you a story. My son's not, I don't think my son's watching this right now. Brian, I get a call from Michael. Hey, Dad, the inspector just turned me down because I just hooked up I added some receptacles to some kind of medical thing, chiropractor, whatever it is. The inspector turned me down because I didn't have this double ground on the receptacles. I'm like, are you kidding me? Did you go to 517.13? Well, the other receptacles in here didn't have the special double ground on the receptacles. I'm like, did you put in a receptacle in a healthcare facility? Yeah. Did you read 517.13? But the plans didn't show. I said, listen, Michael, I don't care if the other receptacles in the space don't have an equipment grounding conductor and a wiring method per 517.13. I don't care if the plans don't show it in there. Anytime you're doing an installation, you have to comply with 517.13 rules. So when you're in this space here and you're putting in switches and you're putting in lights and you're putting in receptacles, then you make sure you go to 517.13a. So I guess that was the question. The answer is, well, yeah, you have to go to 517.13a, but you don't have to put hospital grade receptacles in there. So I wonder what he did. He go, Dad, I got to go. He hung up the phone. He wasn't happy with that answer. The inspector's right. Know your code, buddy. My son's doing fantastic, by the way. If anybody, he's doing amazing. I'm totally impressed. He was a wreck as a kid, I can tell you that. But he's doing great. All right, Brian, what's next?
I think that's it for questions. I do want to put a shout out to the apprenticeship program at Power Design, who is actually doing kind of
Power
watching.
Design, I love you guys.
He's actually starting apprenticeship classes late so that they can watch this before they come into class.
Well, you know what? Power Design is an amazing company. I've been down at their facility and their training center, and wow, what an organization, first class. And so I know they just recently adopted our program. So we're pretty cool and pretty excited about that. So good for them. Brian, listen, I'm done. Did you want to say anything about these guys about how maybe they can get some
Yeah,
a better
absolutely.
experience with
I
what
just
they're
wanted
doing?
to mention a couple of things. We've had a lot of people writing in. Of course, we appreciate this, that are having watch parties where they're inviting friends and watching it together on different social media platforms. We tried comments on YouTube last night. It was a little bit difficult to manage, but we got something in place now for tonight. And guys, I just want you to know I'm actually managing this whole live stream from about 2,000 miles away. And if you guys have been with us since the beginning, you've seen we kind of had to figure out how to do this and had a rocky road. I think we got a pretty good system now. Seems to be working pretty good. But you can watch this on Facebook. You can watch it on YouTube. You can watch it on your MikeHolt.com/live. And you can watch it on your tablet, your phone. Put it on your TV. Why not just go on your TV and go to YouTube or go to Facebook and watch it on your TV? So really encourage you. And if you figure out some really cool new way to utilize a stream or watch a stream or share it with somebody, shoot us an email and let us know what you're doing. We would love to hear how you're using it and how this is helping you out.
Also, listen, guys, at some point this is going to end, right? I mean, you have no clue how much time it takes me to prepare a 1-hour program. And I am terrified all day long. I'm sick to my stomach before we go on live, and I'm hoping everything is going to be perfect. And I think tonight came out to be a little bit better than we've been working on and getting it there. Now, in May, let me tell you what I'm doing in May. If you know an apprentice or somebody who's not licensed or somebody who is licensed, journeyman or master or electrical contractor, an instructor, do me a favor. Send me some questions having to do with the career. Hey, Mike, I'm an apprentice. I'm in a class. Give me some of the dramas, the pain points that you're experiencing. Mike, how do I handle this? And what do I do in the class? Or I'm in the job site, this and that. Mike, I've been in the trade. I was talking to one guy, he's been in the trade 13 years. He calls himself a helper. I'm like, dude, you're not a helper at 13 years old. But if you're not licensed, you haven't done our theory program. You haven't gone through our understanding. You haven't watched our videos. You're not. Listen, you got to take care of your family. So anybody, electrical contractor, you're struggling, trying to figure out, hey, maybe you got a master's license. You want to go into business. Like, Mike, hey, I got some questions. So all those type of questions unrelated to technical, please send them to me because starting in May, and I don't know how long we're going to do it in May, but starting in May, I'm going to be answering those questions. We are going to stay with this time, Tuesday, Wednesday, Thursday. It is 7 o'clock Eastern Standard Time. I think it works the best for everybody. And so God bless. And if you take a look at my slide here, next Tuesday, April 21st, I'll see you.